I know when they beat the Bears.
Yes.
That was crazy. I'm happy the Patriots lost to Miami. Anyway, linear inequalities. Again, not that I think you need a review of this solving-wise. I just want to go over how you represent your solutions. So here we'll start off with an easy one. Example 1, solve. Make sure it's an easy one. Ooh, maybe not so easy. Okay. 2/5 x plus 1 is less than just what you wanted to see this early in the morning, right? Fractions! If you had a good breakfast, then this isn't going to be a problem. Now, the suggestion I made on such a problem when we were talking about 1.5 is still the suggestion I would make here. If you're uncomfortable with fractions, clear them out. Get rid of them. How would one do that? Multiply it all by 5. You want to turn the row there? Exactly. Multiply it all by 5. Quick and painless. Multiply the left side by 5. Multiply the right side by 5. So you're going to get 2x plus 5 is less than 1 minus 10x. You see how easy it is to get rid of fractions? All right, now what? Get the variables on one side, the constants on the other. So I'm going to add 10x, subtract 5, so we have 12x. Now, do I have to flip the sign here? When do I have to flip the sign around? When you multiply or divide by a negative, not when you're subtracting or adding. Divide by 12, and we get the solution x is less than negative. X is less than negative 1/3. Now, depending on what you remember from last year, this is not how I would like you to represent your solutions. Okay? This is inequality notation, which is fine. I mean, it's not wrong. The preferred way of representing solutions when it's an interval of numbers like this is in interval notation. Now, a lot of you, I'm sure, have seen it, but just to be sure, just to be safe, I don't want to assume everybody knows it. Interval notation is more easily found from a number line. So if we were to represent the solutions on a number line, negative 1/3 would be about right here. Open or close circle? Open, because it's not including negative 1/3. So right about there at negative 1/3. And we're going to shade everything to the left. So in interval notation, that's what I'm getting at here. I want your answer represented in interval notation. An interval notation has to have a lower bound and an upper bound. Then they're closed off by either parentheses or brackets. So what's the lower or left bound of our solutions? It goes all the way to negative infinity. That one never has a bracket. It's always a parenthesis. So negative infinity is the lower bound of our solution set. What's the upper bound of our solution set? Negative 1/3. Bracket means included. Bracket is like a closed circle. A parenthesis is like an open circle, so we're going to use an open circle here. And this is how I would prefer that you start to represent all your solutions if it's an interval of solutions. Okay, rather than inequality notation. Use interval notation. Yeah. Just the one in the bottom. If it helps to get the interval, you can draw the number line. But it wouldn't be counted as part of the solution. It would just be this interval right here. Okay. So I don't want to spend too much time on those easy linear ones. Let's do one type of linear. One they'll call it compound. This is still under that subtopic of linear inequalities. Compound inequalities. I am fairly sure that you guys saw these last year, but it's always good to review. So here's example 2. Part A. There's 2 types of compound inequalities that you're going to see. One would look like something like this. -7 is less than or equal to 2x minus 1, which is less than 19. This is called a compound inequality. It's also, I guess, more commonly referred to as and inequality, I suppose. Is it for me?
No.
Let's see, does this go to this person? Or is this for me?
Yeah, just all of it.
Okay. Marissa. This is also called an and inequality, and I'll explain why once we get to the solution. I'm sure you guys remember. Tell me, what do we do?
Add 1 to everything.
Add what? Okay, you're right. What is our end goal, though?
To get x in them.
To get x by itself in the middle. So the only thing we should have in the middle is an x. So we're going to add 1 everywhere. -6 is less than or equal to 2x, which is less than 20.
And divide by 2 and change the sign.
Divide everything by 2. Now we're dividing by a positive. We're not dividing by a negative. So the direction of the inequality sign is actually going to stay the same. So we're going to have -3 is less than or equal to x, which is less than 10. This is why it's called the and inequality, in case you're wondering. Can anybody think of a number that at the same time is less than 10 and at the exact same time greater than -3? Does 0 work? 0 is less than 10 and greater than -0. What's another one that works? 7 works. 6, 5, 4. How many numbers actually work? The answer is actually infinitely many. Because there's an infinite amount of numbers between -3 and 10. But anyway, representing the solution set on a number line. Closed circle on -3 because it's including -3. Open circle on +10 because it's not including +10. And the solutions lie between -3 and 10. They have to be less than 10 at the same time greater than -3. So if you were to shade this, it would be anything between there. Representing this, though, as an interval, lower bound and upper bound, that's what we need. What's the lower bound? -3. But since it's included, we take a bracket. Upper bound would be 10, not included. So it takes a parenthesis. That's one type of inequality, compound inequality rather. It's called the and inequality. Other type of compound inequality would look like this. Yep. If it's not obvious, these are called the OR inequality. These ones you have to solve separate. On the and inequality, you do the same thing to all sides. This one, you got to imagine this word OR is like a big giant barrier. So you're going to solve one inequality separate from the other inequality. You end up with two separate inequalities. So if you add 2, divide by 3, this side you're going to get x is less than or equal to. Sorry, this is strictly less than. X is less than. Come on now. Add 2, divide by 3. Negative 4, right? Over here, if you add 4, you get the solution. X is greater than 11. The reason this has to be called the OR and not the AND
is it's not possible for a number to fit both sides. It can't be greater than 11 and less than negative 4 at the same time. Right? Follow me? That's why it has to be OR. Either a number is greater than 11 or it's less than negative 4, but it can't be both at the same time. It's clear? Squad. Cool. You got any hope squad? No. And other Melissa. Anthony. There you go.
So anyway, when you're graphing this on a number line, you have two separate intervals that aren't connected. You have negative 4, positive 11, you have open circles on both. And it isn't possible for one single number to fit into both solution sets, which is why it's called the OR inequality. Representing this on an interval, you have to have two different intervals because you have two separate shaded areas on the number line. So let's focus the one on the left. Lower bound? The one on the left, what's the lower bound? Negative infinity goes all the way up to negative 4 with a parenthesis. And because both of these are considered part of the solution set, we combine the intervals with the union symbol, union. Now we have to have a lower bound for this solution set here. 11 is the lower bound. Upper bound is positive infinity. So those are two different compound inequalities. Let's see. Hopefully a lot of review from last year. So let's, if there aren't any questions on this, let's move on to quadratic inequalities. These are fun. More fun than linear. And it's all leading up to the most fun, rational inequalities. So, quadratic inequalities. You know what? I got to pause it. All right. Some of you might have seen these last year. Do you want to sign in over there? So, all right. Do you want to sign the target line over there? Thank you. Example 3. We'll start off kind of easy. X squared minus x minus 42. Greater than or equal to 0. If you've forgotten the steps, here they are. At least the method I'm going to show you. There are other ways you potentially could do this with a graphing calculator, but since we don't use them, this is going to be the easiest way to do this by hand. Step 1, get one side to 0. Lucky for you, that's already done. Get one side to 0. Who remembers the next step? I'm sure a lot of you do. If we were solving this as an equation, let's pretend this were equals 0. What would the next step be? Factoring, right? We should try to I forgot what it was. Was it greater than or less than? Greater than or equal to. So the next step is to factor. And I'm going to combine two steps here. Factor and find zeros. What do I mean by zeros? Let's clarify that. Zeros. What makes the factors equal to 0? It would be like the x-intercepts or the solutions to an equation. So factor and find zeros. Let's at least get up to that step there. And then we'll go through step 11. What does this factor into? X minus 7, x plus 6. Good. So then the zeros would be x equals positive 7, x equals negative 6. So once we have the zeros, I'm going to say place on number line and test intervals. And this method right here is going to be the exact same method that we use for the next topic, which is rational inequalities. So this is really good to get used to now on some of these simple quadratic inequalities, because the rational ones ain't quite so easy. But anyway, on a number line, we're going to place the zeros. We have one at negative 6, and we have one at positive 7. Now here's what I mean by test intervals. If I have 2 points on a number line, how many intervals does that break the number line into? If I've got 2 points,
How many intervals are there? 3. There are 3 intervals, right? There's the interval to the left of negative 6. There's the interval between negative 6 and 7. And the interval to the right of positive 7. You guys seeing that? So what you need to do is test
each interval for its sign. Here's what I mean by that. Don't ever choose the zeros themselves, because if you tested the zeros in the original equation, obviously what are you going to get? If you plugged in one of the zeros into the inequality, what are you going to get? 0. That's why they're called zeros. So you don't want to include the zeros. Choose a number in the interval. So to the left of negative 6, what's a good number to use? Exactly, negative 48. No, negative 7 would work fine. Would negative 48 work though?
Yeah.
Anyway, we could choose negative 7. So I'm going to use negative 7 right here as my test point. Now, it doesn't matter the actual numerical value of what happens. All that matters is whether it comes up positive or negative. So don't worry so much about numbers, worry about signs. Here's what I mean by that. If I plug in a negative 7 into this x right here, what's negative 7 minus 7? A positive or a negative? It's a negative, right? If I plug in a negative 7 to this x, negative 7 plus 6 is another negative. But what's a negative times a negative? A negative times a negative, positive. You guys following? Now, is that just a negative 7 that would produce a positive? What if we went a little bit further and did negative 10? Negative 10 minus 7, that's still a negative, right? Negative 10 plus 6, that's still a negative. Any number I chose in this interval right here is going to produce a negative times a negative, which ultimately gives you positive values. I'm going to put a big plus sign in that interval.
Now, I need you to understand why the plus sign. Even though the numbers we're choosing to test are negative, where did the plus sign come from? When I plugged in those test points to the original equation, what came out of that? A positive or a negative number? A positive number. That's why the plus sign. Okay.
Now let's test the number between negative 6 and 7. Anybody think of a really easy one to test?
0.
I'm going to test 0 right here as a test point. 0 minus 7 is negative. But 0 plus 6, positive, right? and a negative times a positive is a negative. So any number in this region from negative 6 to positive 7, any number that you plug in will result in a negative number. So I'm going to put a minus sign above that interval.
Now, just so you can kind of make sense of what I'm doing here and not be so confused. This expression, x squared minus x minus 42, has to be greater than or equal to 0. What kind of numbers are greater than or equal to 0? Positives or negatives? Positives. Positives are greater than or equal to 0, right?
So this test point that I chose, right here, negative 7, or negative 10 for that matter, are those solutions to the inequality? Yes or no? Are those solutions to the inequality?
How do we know that they're solutions? Didn't negative 7 end up making this expression greater than 0? How do we know that? It turned out giving us a positive value. Is negative 10 a solution? What about negative 20? Any number left of negative 6, wouldn't that be a solution? Okay. How come 0 was not a solution to this inequality? It ended up giving us something that was negative. 0 minus 7 is negative 7. 0 plus 6 is 6. Negative 7 times 6 is negative 42. Negative 42 is not greater than or equal to 0, right? So 0 didn't work. Any number between negative 6 and 7 would produce a negative value, which is not greater than 0. Now, you'll start noticing some patterns specifically with quadratic. But just to be sure, let's test the last interval.
Just so we don't make a mistake. If we're going to test 8, for example, to see what happens with 8. Now, even though 8 itself is positive, that's not what we're testing. We need to make sure that it produces positive values in the equation. So 8 minus 7, which is positive, right? 8 plus 6, which is positive. Positive times a positive is a positive. So I'm going to put a big plus sign above that interval. We wanted intervals that produced
Positive values because we have greater than or equal to 0. So, this interval solves the inequality, this interval solves the inequality.
You always have to consider, though, about the endpoints, the negative 6 and the positive 7. Do we include those or not include those? What do you think? We include them, exactly, because it's equal to. So I'm going to put closed circles on here, shade to the left. And shade to the right. So the two intervals that satisfy the inequality, negative infinity, negative 6, bracket union, bracket 7 to infinity. Now this is a way that I want you to do this by hand, but just so we can make a connection to the graphing world, I want you to draw this graph right next to it. You all know the shape of this graph, right? It's a parabola. Is it facing up or down? The parabola's facing up because there's a positive x squared. There's not a negative x squared. What's another word for zeros right here? Somebody said it, right? I think I heard it. X-intercepts, right? We're going to have an x-intercept of 7. Another one at negative 6. So just a rough sketch of the graph would look something like that, right? We don't know exactly right now where the vertex is. We could find the vertex pretty easily, but for what I'm trying to illustrate, all we need to know is where the two x-intercepts are. So we have an x-intercept here. We have an x-intercept there. Above 0 or greater than or equal to 0 means above the x-axis. That's what greater than or equal to 0 is.
So where is the graph above the x-axis? To the left of negative 6 and where else? To the right of positive 7. That's why we have those as our solutions. To the left of negative 6, the graph is above the x-axis. To the right of positive 7, the graph is above the x-axis. So you could also solve these graphically.
And for quadratics, it really isn't that hard to do. But with our rationals that are coming up here in a minute, I don't think you would want to solve those graphically because you have to be able to graph those. And we don't know how to graph them yet. Let's do one more quick quadratic. I'll have you stand up for a minute. Then we best get into these rational ones. So part B, same example. So have you solve 3x squared minus 3x plus then 2x squared plus 4. Go ahead and try that one. We are quickly running out of time, y'all, so we gotta fly through this. From what I heard, most of you started the right way, getting one side to 0. That's not super difficult. So if we get the right side to 0, you're going to have the expression x squared minus 3x minus 4 is less than 0. That factors into x minus 4 times x plus 1. So your zeros are x equals 4, x equals negative 1. I saw most of you get that far, which is good. On a number line, your zeros are negative 1, positive 4. Okay, I'm going to put open circles on them before I forget. Open circles because the endpoints are not included. So I'm going to test a point in this interval, negative 2, for example. I'm going to test negative 2. Negative 2 minus 4, that's negative, right? Negative 2 plus 1, that's negative as well. And a negative times a negative resulted in a positive number. Even though the number I chose to test was negative, when I plugged it into the equation, it resulted in a positive number. It doesn't matter what the positive number was, it was just a positive number, right? Now when you test a number from this interval, 0 for example, 0 minus 4 is negative, but 0 plus 1 is positive, and negative times a positive is negative. Okay. And then when you test a point in this interval, 5 for example, 5 minus 4 is positive 1. 5 plus 1 is positive 6. Positive times a positive is a positive. Question for you. Since we've seen this twice now, positive minus positive, are all quadratic functions going to have that? Positive minus positive?
No.
It isn't. Argue your answer then.
I just thought that when you found the first one, just going to the pattern of, like, for example, it's negative first, and it'll go positive, negative again, or if it's positive first, it'll be positive, negative positive.
That is true. But how come? You are right. Why does it have to follow? It doesn't have to follow this pattern, positive, negative, positive. It could also be negative, positive, negative. Because it's a parabola, right?
This particular one, since it's positive x squared, if we were to look at the graph of this, we'd have an x-intercept at negative 1, one at positive 4. And isn't the parabola going to look something like this? That's why it's positive here, it's minus right through here, and it's positive here. That's why it has to go positive, negative, positive. What would a graph look like that went negative, positive, negative?
It'd be flipped upside down, right? Now think really hard before you answer this next question. Is it ever going to be positive, positive, positive?
Yes.
It can be if it's an imaginary. Then there is no x-axis, so it has no x-intercepts.
What if you were to graph, you're absolutely right, what if you were to graph the parabola and it was way up here?
Where is that graph above the x-axis?
The entire time.
Everywhere. So wouldn't that be positive, positive? It would be positive everywhere? You guys follow it? Now, this one would be an odd problem to give you because its solutions, since they're not real x-intercepts, its solutions would be imaginary. And how would we find them if they were imaginary? You'd have to square root negative numbers. You'd have to use a quadratic formula. But
I'm just trying to get you to realize you're not always going to have like a plus minus plus or a negative plus negative. The entire graph might lie above or below the x-axis, in which case all of it is negative or all of it is positive.
But for your intent on this assignment, you're most likely going to get this kind of a pattern, either plus minus plus,
Just so you can practice factoring, finding intervals. Anyway, which interval do we want here? The plus intervals or the one minus interval here? We want the minus interval because we want our expression to be less than 0. What kind of numbers are less than 0?
that negative interval is less than 0. Less than 0 also means below the x-axis. This is where the graph right here is below the x-axis, between -1 and +4.
Okay. So to represent these solutions, you would say parenthesis -1, comma 4, parenthesis. Questions? Let's hear them. Questions. Why parentheses, not brackets? Not included? Yep, not included. Yeah.
I'm just asking a question because when I was discussing this with them, I didn't understand how it got to x minus 4, x plus 1. So I was just wondering if you can show that just so we understand a little bit more.
The factoring?
Yeah.
It's a good question. X squared minus 3x minus 4. So, to factor this, there's a 1 in front of the x squared. 1 times -4 is -4. We need two numbers that multiply to -4, but that add to -3. Two numbers that multiply to -4 that add to -3. That's going to be -4 and +1. So we take those numbers and split this middle term. So we have a -4x and a +1x. Those came from these two numbers right here, -4, +1. Now that we have four terms, you group. From that first group, you can take out an x. That leaves you with x minus 4. Now from this group, it doesn't appear that they have a common factor, but they really do have a +1, and that's going to leave you with x minus 4.
Why do I need to split the middle term? I mean, I can factor it as is.
You can be simply because there's a 1 in front of the x squared. The reason I'm showing you this process is you're going to have to also do, like if there was a 2 in front or if there was a 3 in front. In that case, you can't just use these two numbers. You have to go through this process. So rather than showing you two different ways of factoring, I will show you the same process of splitting that middle term, just so there's no confusion. Anyway, since x minus 4 is a common factor, you take that out, x minus 4. That leaves you with x plus 1. Okay, stand up, you guys, for like a minute. Stretch out. We've got rationals coming up. All right, y'all. Let's do some rationals. Again, as always, I need you guys to curb your enthusiasm. You're way too excited about this. Rational inequalities. We're going to study how to graph these in chapter, let's see, 3, I believe. Yeah, chapter 3. So it really isn't going to make much sense to show you, well, I can show you graphs, but you don't really know how to graph them yet. So this method of finding intervals and testing points between intervals is really the best way to solve these rational inequalities. So let's just start with an example. So we can go step by step through this example. We're going to solve the inequality 2x plus 6 divided by x minus 2 is less than 0. Let's go through the steps. Step 1 is perhaps the most important of all. It's not the most difficult, but it's the most important. Step 1, one side must be 0, and that's not all, and the other side must be a single fraction. It's really, really important that one side is 0. It doesn't matter where the 0 is. It could be on the left side or the right side, but one side has to be 0. The other side has to be a single fraction. Matter of fact, I'm actually going to go even more simple than that one. We'll get back to that one in a second. What if we just had the expression 1 divided by x less than or equal to 0? Why is it so important that one side is 0 and that the other side
Is a single fraction? When is that true? For what values of x is that true? What about if x is 5? Is that true for x is 5? I'm not really asking you guys some tough questions here. Plug in a 5. Does that make the statement true or false?
False.
So is it true for x equals 5?
No.
Is it true for x equals 20?
No.
Is it true for x equals negative 10?
Yes.
Or for negative 100?
Yes.
That's why it's so critical that we have one side equal to 0, because quite often we're dealing with fractions, right? If I ask you to plug in a 5 for x, will you get 1/5? Okay? Rather than thinking, well, is that greater than an actual number, it's just much easier to tell if it's greater than or equal to or less than or equal to 0, because really all that matters is if it's positive or negative. Is 1/5 positive or negative? Positive. So obviously it's not less than 0. You following? But if I ask you to compare fractions like 1/5 and 2/3, now some of you are pretty good at this, but if you had to compare 1/5 and 2/3, some of you might start to wonder, well, which one's bigger than the other? You understand what I mean? That's why it's so much better to have 0 on one side, because when you compare a fraction to 0, it doesn't really matter the size of the fraction. What matters? Whether it's positive or negative. So these easy questions I was asking you, does 5 work? No. But does negative 10 work? Yes. Okay.
Would that have been easier than if this were the problem? 1 over x is less than or equal to 2/19. Now, if I ask you to plug in 12, does 12 work? Or does negative 20? You understand how it might be a little bit more difficult to see which numbers work? One side has to be 0. One side has to be a single fraction. Okay? Because now all you're comparing is whether it's positive or negative. Now, step 2. This is probably a little more of a difficult step than step 1. You need to find what are called the I can't even spell. Critical. Find all the critical values. Now you need to write down what this means. Critical values are all of the zeros of the numerator and the denominator. Those are the critical values. It's the zeros of the numerator and the zeros of the denominator. So if we take a look at the numerator, 2x plus 6, so we're finding the critical values. When does 2x plus 6 equal 0? It's pretty easy to find. Yeah, subtract 6 divided by 2, the critical value is negative 3. Really easy to find. That's from the numerator. 2x plus 6 equals 0, therefore x has to equal negative 3. We also have to find a critical value from the denominator, x minus 2. When does x minus 2 equal 0? when x equals 2. Okay? So, once you have your critical values, step 3 is just exactly like what happened with the quadratics. Plot the critical values on a number line and test intervals. So I'm going to plot a -3 and a +2. Those are the two critical values. We had a critical value of -3, a critical value of +2.
Now these don't have to follow a specific pattern like the quadratics. It doesn't have to go plus minus plus or minus plus minus. So you have to be absolutely sure that you test every interval exactly.
And not just try to fill it in with patterns. Okay? So I'm going to start all the way to the left. You don't want to test the actual critical value because all that's going to do is give you a 0. That's why they were called critical values. You got to test on either side. So I'm going to test a -4. Plug in a -4 to the original expression, and again, it doesn't matter the actual value. All that matters is whether it's positive or negative. So don't think numbers, just think signs, negative or positive signs. If you plug in a -4, you're going to get a -8 plus 6. What is that? That's negative, right? If you plug in a -4 down here and subtract 2, that's another negative, right? But what's a negative divided by a negative? A positive. Okay, now, just so we can be sure here, -4 produced a positive number, yes? Does that mean only -4 will produce a positive number? What if we went a little bit further and did like, I don't know, -7 over here? What's -7 going to produce? Well, what's -7 times 2 plus 6? What is that? That's a negative. -7 minus 2 is another negative, right? Negative divided by negative is any number I choose in this interval is going to result in what type of a number? Always a positive number. Okay? That's why you only really need to test one number in the interval, because whatever the sign of that number turns out to be, every number in that interval is going to produce the same type of number, in this case positive. Okay? So, between -3 and 2, again, you can't just assume because this one is positive, this one's going to be negative. It doesn't have to be. Often it is, but it doesn't have to be. So, what are we going to test? 1 or 0. You can test 0. 0 is pretty easy. So 2 times 0 plus 6, which is positive. Yep. 0 minus 2, however, is -2, and a positive divided by a negative is a negative. So if you plugged in a 0, it resulted in a negative number. That
ensures, and you need to believe this, any number in that interval from -3 to 2, any number plugged into there will result in a negative value.
Okay, that's why we only have to test one number. Now 2, +2. Anything to the right of that would work. So let's do 3. +3. What are we going to get if we plug in a 3? Positive up there. Positive down there. Positive divided by positive is a positive. So now that we've determined the sign of each interval,
We just got to choose the correct interval. Look at the original problem. That expression had to be less than 0. Where is that expression less than 0? From -3 to +2. That's where the expression produced negative values. That means less than 0.
open or closed? It's an open interval. So it's going to be parenthesis -3 to 2. Now they do try to not trick you, but just see if you're paying attention. what's your very, very, very first impulse? I want you to answer as quickly as you can. If I were to put an equal to underneath that, what would that change on the problem?
The immediate thought is to close both intervals, right? With brackets, why would that be incorrect here? Exactly. The first impulse when you see that equal to is to change both of them to brackets. The problem is, can you include positive 2 as part of your solution? What's 2 minus 2 there? 0. You can't divide by 0, so in this case, the right side would still have to be a parenthesis. The left side would be a bracket. It's something to watch out for. You can't ever include anything that's going to end up with an undefined expression.
All right, let's do. Oh, I did want to do one problem from chapters 1.6. That's on the review. All right, I'm going to stop here, but I'll start with another one of these on Wednesday.